Okay, this is May 2015, paper 1, time zone 2, question 13. And it's an induction question. So these parts are going to be relevant as we go through. So for part A, show that 1 over root of n plus root of n plus 1 is equal to this thing here. And especially when you look at this negative here, you should be thinking, this should remind you of complex conjugates or rationalising denominators. And it's essentially the same thing. In fact, it's exactly the same thing. We want to rationalise the denominator, and it turns out when we rationalise the denominator, it's going to rationalise to 1. So let's multiply top and bottom by root n minus root n plus 1 over root n minus root n plus 1. Whoops. If you do that on the top, you get root n minus root n plus 1. And if you do it on the bottom, you get root n times root n, which is n. You get root n times root n plus 1. Root n times n plus 1. You also get minus root n times root n plus 1. So in fact, that cancels out, which is the whole point. The square root bit vanishes, and minus root of n plus 1 times root of n plus 1, which is n plus 1. Which gives you root n minus root n plus 1 all over negative 1, which equals the answer that we're given, which equals root n plus 1 minus root n q13. Part B asks us, hence show that root 2 minus 1 is less than 1 over root 2. So I'm going to use the result from before. Root 2 minus 1 is the same as root 2 minus root 1, which is the case from above where n is equal to 1. So that means it's equal to 1 over root 1 plus root 2, or 1 over root 2 plus 1. Now root 2 plus 1 is bigger than root 2, so 1 over root 2 plus 1 is smaller than 1 over root 2. The bigger the denominator, bigger denominator, the smaller the reciprocal. So that's that done. QED. Okay, let's have a look at the meat of the question. Prove by mathematical induction that the sum of 1 over r is greater than n for n is greater than or equal to 2. Well, so we're going to start with our base case, which is n equals 2. n equals 2 gives us the sum from r equals 1 to 2 of 1 over root r, which is just 1 plus 1 over root 2, which is bigger than root 2, which can be rearranged to, let's take 1 off both sides, take 1, 1 over root 2 is greater than root 2 minus 1, which we saw in part B. So therefore P of k, P of 2 is true. Proposition is true when n is 2. Okay, now for the more involved bit. We want to assume that P of k is true. So that is assumed that if you add up all the numbers from 1 to k, 1 over root r that is bigger than the square root of k. So let's assume that is true. I need to show that the sum from 1 to k plus 1 of 1 over root r is bigger than the root of k plus 1. So let's start by adding one more term. Adding the k plus 1th term to both sides. So the k plus 1th term is going to be 1 over root k plus 1. Add that to the left side, you get 1, thus and now the sum goes up to k plus 1. Add it to the right side, and you get root k plus 1 over root of k plus 1. Now I'm going to take a little pause here to point out a common error. The common error is to try and prove that that is the same as that. Unfortunately, that's futile because those two things are not the same. So, instead, what you need to be proving is that these two red blobs, this red blob is bigger than this one. So I might even write that down. I need to show that root k plus 1 over root k plus 1 is bigger than root k plus 1. Alternatively, that's equivalent to root of k plus 1 minus root k being smaller than 1 over root k plus 1. But in part A, we saw that this was equal to 1 over the root of k plus the root of k plus 1. Now that is definitely smaller than 1 over root of k plus 1 for the same reason we were saying before. The denominator is bigger. This denominator is bigger than this denominator, so the fraction, the gold fraction, is smaller than the black one. So, it's all in separate pieces now. So this is true. Since that is true, that implies that the sum from 1 to k plus 1 of 1 over root k is bigger than the root of k plus 1, i.e. proposition k plus 1 holds. And then it's just a case of writing your induction sentence here. Therefore, since P1 holds, wasn't P1, sorry, was it? I don't know if you can see this as I'm typing it, probably not, so it's just all going to appear at the end. Since P2 holds and P of k implies P of k plus 1, by induction, Pn is true for all n greater than 2. For n greater than or equal to 2. That's all I'm supposed to say. Like that.